This paper, Using Conditional Independence for Belief Revision, is joint work with Jim Delgrande and Pavlos Peppas. So the motivations that we're considering belief revision. And in belief revision, we have some existing beliefs, we have some new information to revise them by, and we wish to produce an updated or revised belief state such that we maintain consistency and we minimize change to the existing beliefs to the greatest extent possible. Now, writing down what exactly is meant by minimizing changes to existing beliefs is a little elusive. One idea put forth by preex is that we should postulate that those beliefs that are relevant to the new information we're revising by must be left unchanged. This is interesting from the perspective of minimizing change. It's also interesting from a computational perspective in that belief revision operators that adhere to this postulate could very well work in such a way that they don't even take into consideration irrelevant beliefs and thus reduce the amount of work they have to do. So our concern is that in existing literature, the notion of irrelevance is very, very, very restrictive, and we suspect that it's so restrictive it may not apply in many cases. So our contribution is that we argue that multivalue dependencies can serve as a useful generalization of the existing notions of irrelevance, in a sense similar to moving from independence in probability theory to conditional independence. Multivalue dependencies will let us move from unconditional irrelevance to conditional irrelevance. And we will generalize preex postulate by introducing classes of belief revision operators which comply with a multivalue dependency in a suitable sense. Further, we offer characterizations of these classes of operators in terms of conditions on their associated faithful rankings, and using these conditions we can show that such operators exist. So our setting will be propositional logic. We'll fix a finite vocabulary V and we'll generate a language from it in a standard way. We will use the variables u, v, and w to range over possible worlds, which for us are just truth value assignments. And we're going to identify these truth value assignments with the conjunctions of the literals they satisfy. So the example here is that the truth value assignment that maps P to true and Q to false is more or less the same thing as the conjunction of P and not Q, at least for us. We will use the square braces around a formula to denote the possible worlds satisfying that formula, and we will write v of phi for the minimal set of variables required to express the formula. So the example here is that v of p and q are not q, despite the formula containing both p and q. V of this formula consists merely of p, because of course we can rewrite this formula to contain no occurrence of q. So the other ingredient we need is what we mean by belief revision operator. For this we will adopt the Katsuno-Mendelssohn approach of saying that it's just a binary function that takes a formula that represents the existing beliefs paired with a formula that represents the new belief, and it produces a formula that represents the resulting revised belief state in such a way that it satisfies, well, the basic postulates, namely, if we revise by something, we should end up believing that thing. If it's consistent to form the conjunction, all revision should amount to is forming the conjunction. If we produce an inconsistent belief state, well, then we must have had to revise by something that was inconsistent. That's the only excuse acceptable. And R4 tells us that everything has to be invariant under logical equivalence. Further, we're going to restrict attention to belief revision operators that satisfy the supplementary postulates R5 and R6, which can just be thought of as an attempt to pin down a little more what is meant by having minimal change. So the other thing we need is the notion of a faithful ranking. So a faithful ranking for knowledge-based K is just a binary relation on possible worlds that orders those worlds by increasing implausibility from the perspective of K. So more precisely, it needs to be transitive, it needs to be total, and it needs to be such that the minimal worlds under the faithful ranking are exactly the models of K. Now, the interesting thing is the Katsuno-Mendelssohn representation theorem that tells us that one of these binary functions is a belief revision operator satisfying the supplementary postulates if and only if we can write down some family of faithful rankings such that, semantically speaking, to revise K by phi, All we have to do is take all of the possible worlds satisfying phi which are minimally implausible from the perspective of k. And it's actually quite easy to write down one of these faithful rankings. So an example here is just we could say everything that satisfies k is the least implausible, and then we'll have one more level of implausibility that will have all of the non-satisfying possible worlds for k. So the other ingredient we need is the notion of a multivariate dependency, which we take from database theory. So given a formula phi and a subvocabulary x, we'll define the projection of phi onto x up to logical equivalence. It's a unique formula so that the models of the projection are just possible worlds that agree with some possible worlds satisfying phi on the subvocabulary. So basically we're removing all of the constraints on the variables not in x. And the notion of multivariate dependency is defined by saying that phi satisfies the multivariate dependency x mvdy if and only if we have this decomposition that we can project onto x and y, and we can project onto x and the complement of y, and if we take the conjunction, this gives us back the original formula. Note that the complement of y will always contain x so long as we assume x and y are disjoint, which we will. So I will just write this decomposition a little more simply in the future. So the example here is that this knowledge base P implies Q and Q implies R satisfies this multivariate dependency Q MVDP, and one can just compute it out and it works. Whereas it does not satisfy this if we switch the roles of P and Q. Okay, so another notion of irrelevance which we could adopt would be Darwish's logical conditional independence. There's a ton of different ways of formulating this. A definition I particularly enjoy is to say that y1 and y2 are independent given x modulo k, if and only if, whenever we write down formulae phi1 and phi2, phi1 being contained in y1 and phi2 in y2, and we choose some possible world so that k and the projection of this possible world onto x implies phi1 or phi2, then one of these two disjuncts was just implied outright. So one theorem is it turns out that k satisfies this multivariate dependency x mvdy if and only if y and the relative complement of x and y bar are independent given x modulo k. So we could work with Darwish's definition. The theory would work out the same. The other thing worth noting is that k satisfies multivariate dependency if and only if we have k1 and k2 with the vocabularies restricted in the appropriate way, such that k is equivalent to the conjunction. So really, we have three perspectives. We either can satisfy multivariate dependency, we can satisfy an independence property in the notion of Darwish, or we can have one of these sort of syntax splittings. All right, so now let's talk quickly about the unconditional case of preex postulate. So one of the problems is that the Katsuno-Mendelssohn postulates don't really enforce minimal change. We can look at this belief revision operator, which just throws everything away from the existing beliefs if there's a conflict, and this is not ruled out. So this would motivate one to introduce something like preex postulate, which says that if we have some syntax splitting of our knowledge base into K1 and K2, which are over these different disjoint vocabularies, and we want to revise by some formula that's specific to Y1's vocabulary, then we can just do this belief revision locally. We'll revise K1, we leave K2 unchanged, using some belief revision operator restricted to this language Y1. So Delgrande and Peppas argue that irrelevance really is not this syntactic phenomenon, it's semantic. It's a domain-dependent notion, and writing down which irrelevancies are worth thinking about is actually part of the knowledge engineering task. It's part of the specification of the domain. And once we've written them down, we can ask that a belief revision operator complies with one of these irrelevancies in the sense that we'll say it complies with here empty set MVDY if the following holds. Well, if we have any consistent knowledge base that satisfies this multivariate dependency, and we choose some formula revised by over y, then our revision has this nice decomposition. So now to get to the real contribution of this work, conditional relevance. So suppose we have an agent that knows about birds, refrigerators, and wind turbines. And the agent knows that birds are killed by wind turbines and wind turbines power refrigerators. In preex paradigm, birds and refrigerators are going to be deemed relevant. However, we would argue that birds and refrigerators should be suitably irrelevant, that we should be able to somehow get one of these decomposition properties for doing belief revision. And that's going to motivate us to write down some multivariate dependencies: turbine vocabulary, MVD bird vocabulary, turbine vocabulary, MVD refrigerator vocabulary. And the idea is that we're going to formulate notions of a belief revision operator complying with these dependencies, which would ensure that in some sense birds and refrigerators will be treated as irrelevant during belief revision. So our first notion is that we can say a belief revision operator partially complies with x MVD y when the following holds. Well, given a knowledge base k that's consistent and satisfies our multivariate dependency, and a formula to revise by which is consistent and constrained to the subvocabulary y, then our belief revision can be expressed as just revising by this formula, projecting onto x and y, and then taking the conjunction with the projection of our original beliefs onto y bar. So note that following partially compliant revision, the irrelevant beliefs in k projected onto y bar are left unchanged, and moreover, the underlying multivariate dependency continues to be satisfied, so we've preserved this as well. So in terms of the characterization results, we're going to look at faithful rankings, and we're going to say that a faithful ranking partially respects a multivariate dependency if either the knowledge base does not satisfy the multivariate dependency, so we don't have to make any promises, or we have a number of conditions are satisfied. The first one saying that if we have two worlds that agree on x and y, and on the basis of y, k rules out u, but k projected onto y bar has no problem with u, then if v were strictly preferred to u, there must exist some world w that agrees with u on y, which is strictly preferred to v. And we have our second ranking condition, which says that if we rule out a world on the basis of ky bar, then we can find some world that's compatible with ky projected onto y bar, which agrees with u on y, and u is strictly preferred to v. So our theorem here is that if we have a belief revision operator and some family of faithful rankings that defines it in the suitable sense, then our belief revision operator partially complies with the multivariate dependency if and only if each faithful ranking partially respects it. So using this, we can prove that such an operator exists. So just as an example construction, given a knowledge base that satisfies a multivariate dependency x MVD y, we can define this ranking function on possible worlds, where we'll say that the best worlds are those that satisfy k. The second best worlds are those that, while they may not satisfy k, they're perfectly consistent with k projected onto y bar, and the worst worlds are those which can't make either of these guarantees. And we can define a faithful ranking by just taking the ordering that's induced by this ranking function, and this will satisfy PCS1 and PCS2. So if we just arbitrarily choose the other rankings to make up a whole family of faithful rankings, the corresponding belief revision operator will partially comply with x MVD y. So as another example, if we define rankings, well, using sort of the trivial ranking example from earlier on, this will satisfy PCS1 but not PCS2. It's possible also to make an example that satisfies PCS2 but not PCS1. So these conditions are independent. So now let's talk about fully compliant belief revision. So consider again birds, refrigerators, and wind turbines, and suppose we change our belief that wind turbines kill birds, instead say believing that birds have learned to avoid turbines. This is certainly consistent with our existing belief that wind turbines can power refrigerators, so there's no reason for that belief to change, but partial compliance is not strong enough to guarantee this for us. So we're going to define what it means then for a belief revision operator to fully comply with a multivariate dependency. It's going to essentially be the same thing. The only difference, though, is now the formula we're revising by can involve the shared vocabulary x, and we have only the price to pay for this flexibility, the constraint that we must revise by something that's consistent with k projected onto y bar. And under these circumstances, we will have the same decomposition. And it's worthwhile noting that fully compliant belief revision operators are clearly also partially compliant. So, a characterization result. We can define what it means for faithful ranking to partially respect the multivalue dependency. We have a number of conditions. I would say that what's less important is understanding what the conditions say so much as that they exist, they can be written down, though they are admittedly a little messy. And our characterization result is that a belief revision operator defined from some family of faithful rankings is such that it fully complies with the multivalue dependency x MVDY if only if each of the faithful rankings fully respects it. And returning to our example for partially compliant belief revision operators, we find that the same construction actually gives us a fully compliant belief revision operator. So, in conclusion, multivalue dependencies generalize preex syntax splittings to capture conditional relevance rather than just the unconditional irrelevance considered in preex work and its further developments. Partially and fully compliant belief revision operators generalize the Delgrande Peppas approach to preex postulate. They admit characterizations via conditions on their associated faithful rankings, and they exist, though it does remain open to find interesting examples. Thank you for listening.